All right, finally, start of lecture now is a major technology performance. All right, so we're going to move on to this next chapter. But before we move on, are there any questions from the last chapter? Good. It was kind of a whirlwind overview, and we covered a big distance, about 2 inches deep. Yep.
So the main, context of chapter 1 was just, the 5 themes, right? Those 5 themes.
There were the 5 themes, the 5 threads in biology. Yep. There was what life is, definition of living organisms, scientific method, and evolution. Were the main parts. Okay? So again, we covered, a mile wide and 2 inches deep. We went, kind of quickly. We didn't go into a lot of depth. Now we're going to start to cover specific topics in a fair amount of depth. Okay? Everyone okay with that? Now, again, I want you to take good notes, really good notes. If you find yourself sort of sitting back and you haven't written anything in a while, that's a good indicator you need to take some more notes. All right? Now, the lectures are recorded. I told you there's a YouTube channel with a video recording of the lecture. And now what I'm going to start to do is record the audio over the PowerPoints. So you've got both of those options. All right? But still, take really good notes. What you don't want to do is have to sort of go back and relive the entire lecture again, unless you need to. All right? Okay. So, chapter 2, we're going to start to have a look at chemistry. Has anybody had a chemistry class already? All right, a couple of you. So some of you are going to find this a breeze then if you've had a chemistry class. All right, some of it's going to be review, and we're probably going to cover it in a little more surface, not as much detail as in your chemistry classes. Yeah. So in some ways, this chapter in a chemistry class, which I'll cover in about a week or week and a half, you guys take maybe half a semester to do. So you're going to cover it in a lot of depth. So I'm going to gloss over a lot of details in terms of the chemistry. All right? But I'll give you enough chemistry so you can understand the biology that we're going to talk about afterwards. Everyone okay with that? Yeah? All right. Okay. So let's think about this. Matter consists of chemical elements in pure form and in combinations called compounds. All right. So organisms, you, are composed of matter. In fact, anything that takes up space and has a mass is composed of matter. The desk you're sitting at, the chair you're sitting on, the air around you is all composed of matter, and so are you. So from a biology context then, every living organism is composed of matter. Everyone from a human being right down to an HIV virus. All composed of matter. Matter itself is made up of elements in pure form or combinations of elements that make compounds. Okay. All right, so let's have a look at this then. What do we got here? Ants. Good. And what are the ants doing? What's going on there? What does it look like? Is it raining on the ants, or? A ladder, kind of looks like it. What do you think that stuff is? Is it something raining down on them, or? Sorry? Yeah, they're shooting something out of their abdomens. Okay? So some ants, when they want to protect the colony or their host plant or some other resource, as a defense, they employ chemical weapons. And they spray jets of formic acid at whatever's trying to attack them. All right? And they're really good at it. In fact, there's some ants in Costa Rica that form a mutualism with a tree. They live in a little cavity in the tree stem. And when anything, like an insect, gets on the tree, they come out that cavity and they attack it by spraying formic acid. In fact, they're so defensive, you can put a paper clip on the leaf. And they'll spray it, and they'll keep spraying it. And that paper clip goes very rusty as a result of the formic acid. They're really good at defending. All right, so let's have a closer look at formic acid then. Formic acid is a pretty simple compound. There's its chemical structure. So we're going to dissect that apart a little bit so you can understand it. So there's formic acid. So we've got an H, an O, an O, an H, and a C for carbon. Okay, so that's C right in the middle. That C stands for a carbon atom, one carbon atom. Now the lines, those straight lines, they represent chemical bonds. All right? So we've got a carbon atom that is bonded to an H, which stands for hydrogen, a hydrogen atom. And then we've got a carbon which is bonded to a O for oxygen. All right. And that O for oxygen is bonded to an H for hydrogen. All right. And the carbon, oh, what does it mean if I've got two lines then? It's two chemical bonds. This is one chemical bond. There's two chemical bonds, which we call a double bond. All right? Now, the particular chemical bond that these lines represent is called a covalent bond. And I'll go into that in a lot more detail a bit later. So that's double bonded to an oxygen.
Only the double bond or covalent bond, or all of them?
Every straight line is one covalent bond. One covalent bond. One covalent bond, another covalent bond makes it a double bond. One covalent bond, one covalent bond. Right, let's have a look at this for a moment. There are some patterns. Anybody notice any patterns? Anything that's like predictable, a pattern. Anything that's repeated. Right, there's a lot of H and O. There's two O's, two H's. That's repeated. The carbon, it is, but that's not really a pattern, right?
There's an O connected on each bond. Like, the double bonds go, yeah, so that's connected down to the C and then to the H. There's an O and an H on each bond.
Okay, I'm not exactly sure I see what.
I don't know.
All right. What you got?
H's have one bond and the oxygens have two.
Good. That's the pattern I'm looking for. Both H's make one bond. H's, hydrogens, only ever make one covalent bond with another atom. Good. Right, and we'll talk about that. So, oxygens make how many bonds? Two. 1, 2, 1, 2. There. It's predictable. Two bonds, one bond. All right, now, if you were to take a guess, how many bonds would you say that carbon always makes? How many? 1, 2, 3, 4. Good? And carbon, in fact, does always make 4 covalent bonds. Good? All right. What's the chemical formula for water? H2O. There's the O. Let's connect them to two hydrogens. Oxygen makes 2 bonds. Hydrogen makes 1 bond. Hydrogen always and only ever makes 1 bond, covalent bond. Oxygen makes 2 covalent bonds. Carbon makes 4. Do you reckon there's an element, an atom, that only ever makes 3? Yeah, there is. And it's nitrogen. In fact, that's a little bit of a lie, because sometimes nitrogen makes more than 3, but let's keep it simple. All right. Okay. So do you kind of get the hang of things? Yeah? And I'm going to explain a lot of this. All right. So I do want to explain something in this second graphic I put up. Where's the carbon? Where's the C for carbon? It's gone, isn't it? It's in the left one. So sometimes what we do, just to keep it simple, is we can leave out carbon sometimes because it's so common in biological molecules. So in the second one, you can see that there's those 4 bonds all coalesce on that center point, don't you? Even though the C is not there, you know that there's a C there, right? Because bonds only bond one atom to another, not one bond to another. Does that make sense? Yeah?
So it's like implied.
Yeah. It's like, let's just keep it simple, we'll leave it out. You know it's there. There are 4 bonds all coalescing. Bonds don't bond with other bonds. They bond atoms together. Carbon makes 4 bonds. Yeah.
Is that the same reason why there's no covalent bond between the last oxygen and hydrogen?
So, yeah. Next thing, that's exactly what it is. Yep.
So you know oxygen has 2 and hydrogen has 1.
Absolutely. So let's draw this a bit more efficiently. We can even say, well, we don't need to draw that. We're going to put these 2 together. You know that atoms are connected with bonds, right? They're all connected with bonds in a molecule. And so let's just leave it out for the sake of simplicity. We'll put them next to each other, but you know that they're bonded together with 1 bond. Is everyone okay with that? It's just a simpler way of drawing that molecule. Yep.
So a compound element is a molecule.
A molecule is 2 or more atoms joined chemically with a chemical bond. That's what a molecule is.
That doesn't know the same atom.
It can be the same atom or it can be different atoms. So we're not jumping the gun a little bit. These are awesome questions. I'll talk about that, I promise. But to answer it, there's a hydrogen molecule, right? Because it's 2 hydrogens bonded together with a chemical bond. That's what makes it a molecule. 2 or more atoms joined with a chemical bond. Okay? This is a water molecule. Okay? 2 or more atoms joined together with a chemical bond. In this case, we happen to have, in the same molecule, 2 different elements. In this molecule, we've got 3 different elements. Does that answer your question?
So chemical or compound. Sorry, compound.
So a compound, then, is a molecule which has more than 1 element. Compound, element.
Because there's different
Because
types.
there's 2 different types. Like
So we've got-
hydrogen and
Yeah, we've got 2 different elements in the same
so
molecule.
that makes it a compound.
That's right.
Okay,
Good?
got it. Yeah.
Good.
So without actually showing that bond between the oxygen and the hydrogen, that doesn't change it, because isn't that hydroxide?
It's a hydroxyl group, but a hydroxyl group is O chemically bonded to an H. And we can just sometimes write it like this. Okay? We're lazy in science. We don't like to write more than what we have to. So it's like, ugh. We know that if these together, that's always the case. We know that if we've got 4 bonds coalescing, there's always a carbon there. It's just a convention. It's a predictable convention. Okay? All right. And then we can take formic acid and we can just write the chemical formula of it. Now, that's the chemical formula of the molecule, and it's also a compound. All right. So let's take formic acid, and we're going to do CH. So there's the chemical formula for formic acid. So in the chemical formula, we can account for all the atoms in the molecule. 1 carbon. 2 hydrogens. See the H2? 1, 2. 2 oxygens. 1, 2. Good? Okay. Now you know what ants squirt. All right, so let's start by taking a look at elements and compounds. All right, and we'll explain and define them. So matter is made up of elements. Okay? Anything that has space and mass is matter, and it's made up of elements. Now, an element is a substance that can't be broken down into any other substances by chemical reactions. So, for example, if I take hydrogen, hydrogen's an element. I can't break it down into anything else with a chemical reaction. Hydrogen is hydrogen, and it's an element. If I take oxygen, there's an oxygen molecule, oxygen's an element. I can't break this down into anything else with a chemical reaction. Okay? Now, there are nuclear processes and reactions that can change elements into other elements. All right? But by chemical reactions, we can't. So an element then is a substance that can't be broken down into anything else by chemical reaction. If I give you a chunk of an element, it's made of one atom type. Okay? So if I gave you a jar filled with hydrogen, and I said, well, there's the element hydrogen, and I could get rid of all of the other atoms in there except hydrogen, then you'd have hydrogen in its pure form, elemental hydrogen, and only hydrogen. Okay? And we can't break it down into anything else. And we've got 92 naturally occurring elements. And you've got to remember all of them. I'm kidding. You don't. There's a bunch that I do want you to remember. All right? It's a handful of the 92. Go take some chemistry classes, and I think they want you to remember all 92 of them. All right? So if you have a look at this table up here on the wall, that's called the periodic table, and it lists all of the elements, the naturally occurring ones, and we've actually got some man-made elements. Now, in biology, we're going to focus mostly on these ones up here and a few of these down here. All right. So there we've got H for hydrogen. There we've got O for oxygen. There we've got C for carbon. And between oxygen and carbon is nitrogen. They are 4 really important elements in biology. All right? So we're going to talk about them a lot. Okay, and then we've got some other ones. I don't know, what other ones should we point out? What is Fe? Iron. Isn't it nice? H, hydrogen, C, carbon, O, oxygen, N, nitrogen. Why isn't iron I? It is ferrous, ferric, Fe, but also I has already been taken over there by iodine. Iodine's the right way to say it.
Oh, okay.
Just so you know. All right. Okay, let's have a look at some more. Ooh, what's Na?
Sodium.
Good. What's K?
Potassium.
Potassium. What's Ca?
Calcium.
Good. What about, what's Al?
Aluminum.
What?
Is there another way to say it?
What is it? Good.
Ooh.
So guess what? There's an organization called IUPAC. And it's an international organization made up of representatives from every country, including the United States. And they decide on these conventions. They decide on the spelling of element names, so everybody's on the same page, right? Worldwide. And they decide on what symbols are used and other conventions in chemistry, IUPAC. Now, here's what IUPAC said. You ready for this? The substance, aluminium. The element, aluminium, which is Al, must be spelled like that. That's the correct spelling for it.
So it's just pronounced differently?
No.
Oh, no, it is definitely spelled differently.
Yeah. Here's what you do in America, right?
That's funny because I have a sticker.
You do this. Here's what you did. You said, let's just leave out the I. Let's not even worry about it. Let's get rid of it. Many other elements end in IUM, don't they? Calcium, sodium, potassium. There's a song there somewhere, isn't there? Yeah?
We can make one.
You could totally make one. That might be a good extra credit assignment, right? I tell you what my kids like to do.
I got a guitar. Or,
You do? Are you musical?
uh,
Do you like to perform?
not right now.
All right.
I remember I told you about a song that I knew and I wasn't going to sing it, so.
All right.
I
Okay.
don't remember what song
Make one up with the IUMs and some sort of rendition of aluminium, aluminum. That'd be kind of funny. My kids like to make words from the symbols for elements in the periodic table. And there's whole websites devoted to the longest words you can make with the symbols for the elements in the periodic table. It's a really good, fun way to learn, I've got to tell you. Maybe it only works with, I don't know, freshmen at high school or middle schoolers, but it's a fun way to learn. All right, so you guys have dropped the I in common use, but in the scientific community, it's aluminium. Does anybody know why you dropped the I? It's the only country in the world that has. No? Here's what I heard. I don't know if it's true or not, but I did a little bit of research, and here's what I managed to come up with. So aluminium is a remarkable metal. It's very strong and very light, but it's also difficult to refine. It's refined from an ore called bauxite, and it takes a lot of energy, power, to refine it. And so it wasn't until early in the 1900s that there was enough energy, cheap energy, to refine it and make it something that could be mass-produced. All right? So as soon as it was able to be refined cheaply and mass-produced, it was this new thing. It's like, well, let's make sure everybody uses it. So there was a big advertising campaign launched in the US to launch this newfangled substance, aluminium. But, of course, the advertisers weren't scientists, and they made a spelling mistake and left out the I. And after that, it became aluminum. That's the story I heard. So spelling is important. All right. So lots of other elements up there. All right. What's Zn? Zn.
Xenon? Was it zinc?
Zinc.
Okay.
It is. Yep. He. Anyone know what He is? Helium. Good. What do we use helium for?
Balloons.
Balloons. That's right. And you suck it in and you talk funny. Yeah. You must have done that. All right. Okay. So we've named a bunch of the elements. You're familiar with them already, by no means all of them, but I want you to be familiar with the ones that are important in biology and that we're going to talk about recurrently. Okay? All right. So a compound, then. A compound is also matter. Yeah, all compounds are matter. So a compound is a substance that consists of two or more elements. And the atoms of the element are typically chemically bonded together. So here we've got a molecule of an element. Here we've got a molecule of an element. Here we've got a molecule of a compound. You know it's a compound because
Water.
two or more elements. Yeah, two or more elements. What's formic acid? Is it a compound?
Yes, it is.
Yeah, it is. All right. What about this one? What's that one? Carbon dioxide. Is it a compound?
Yes.
Yeah, it's a compound. All right. Ooh, here's another good one for you. Is it a compound?
Oh, yeah.
It is. What's the name of that substance? Methane. That's the right way to say it. Methane. Yeah, not methane.
Okay.
I don't know who came up with methane. It's definitely methane.
We love it.
Okay, so let's have a look at another compound. Let's have a look at table salt, all right, which is sodium chloride. We've got an Na, which is a sodium, and the Na stands for natrium, or you call it sodium, and the Cl stands for chlorine. And when a sodium atom is chemically bonded to a chlorine atom, we'll talk about this bond, but we call this part chloride. That's why we go sodium chloride. All right, sodium and chlorine chemically bonded together form sodium chloride, which you're familiar with as table salt. Yeah. All right. So that's a compound. You know it's a compound because
I have two or more elements.
yeah, two or more elements. Can compounds have three elements in?
Yeah.
Yeah, 4,
Yeah.
5,
Yes.
for sure. All right, so sodium is a really cool substance. And I remember in the equivalent of high school when I was growing up is the chemistry teacher brought out a little chunk of sodium, right? We'd never been exposed to sodium before. We'd heard about it because it was in sodium chloride. But sodium is a soft metal. Doesn't that sound crazy? It's a soft metal. You can cut it with a knife. It's that soft, right? Not quite as soft as butter, but you can cut it with a knife. And sodium itself, the element sodium, is like a silvery, shiny silvery color. But it's super reactive. So as soon as you cut it, it immediately reacts with the oxygen in the air, and it forms an oxide layer, and that's why this looks grey. Okay? But if you cut it really quick, you can see that silvery color. It's cool. Metal. Soft. Chlorine, the element chlorine, is a green, nasty smelling gas. All right? Now, bleach, sodium hypochlorite, gives off chlorine. So chlorine kind of smells a bit like bleach. All right? But it's a green, smelly gas. So sodium reacts with chlorine. In fact, as elements, they're both super reactive. And they react together to form sodium chloride, that white crystalline substance that you're used to. Yep.
Aren't they also a little poisonous?
So yeah, they're poisonous because they're so reactive. All right. All right. Doesn't that seem remarkable that you can take a soft silvery metal, react it with this green smelly gas, and you get white crystals that non-toxic, very stable, right? And they dissolve in water. It's quite remarkable, isn't it, when you think about it? So, sorry? I know. If you put sodium in water, you get a mini explosion. All right? It's so violently reactive. That's all that's all an explosion is. It's a very violent chemical reaction, unless you're talking about a nuclear explosion. But okay, so put sodium in water, and it can it kind of can burst into flames. Put potassium in water, and that's really fun, I tell you. You see this sort of fireball zipping around on the surface of the water. It's awesome. Kids love it, right, in their chemistry classes. It's what they use to hook people in. All right, so we can think about the properties of sodium chloride as being emergent properties, properties that the compound has that both elements together don't have. So now let's think about water. Or if I go to a restaurant and they say, what do you want to drink? I'll say water. And they'll say, and I'll say water. And they'll say, and I'll say water. And they've got it. All right? Okay, so water or water. You know what I'm talking about, don't you? All right. Okay. What are the properties of oxygen? Oxygen itself, well, I wouldn't say oxygen's flammable. In order for something to be flammable, you've got to have something with oxygen, and then it can be flammable. What are the properties of elemental oxygen? Does it have a color? Doesn't. It's colorless. Does it have a smell? No, it's odorless. And what's its state? Gas. It's a colorless, odorless gas. In fact, roughly 20% of the air around you is oxygen, elemental oxygen, oxygen molecules. Good? What are the properties of hydrogen? Does it have a color? Doesn't. Does it have an odor? Doesn't. And what's its state? It's gas. It's a colorless, odorless gas. All right? So, join them together and we get water. Now, water is colorless. It's also odorless. It's a liquid, though. Very different from these two elements. Again, you can think about that as another emergent property. Okay? All right. Think about formic acid. It's got hydrogen, colorless, odorless gas, oxygen, colorless, odorless gas, and carbon. Carbon can take a couple of different sort of forms or states. But diamond, if you've got a diamond on, have a little look. And that's basically elemental carbon. That seems crazy. You can combine carbon from a diamond 2 colourless odorless gases, and you get formic acid that ants use to get predators and parasites away. All right. I jumped the gun a little bit. Okay. So about 20 to 25% of those 92 naturally occurring elements are essential to life. And we call those the essential elements. And we're not going to talk about all of them, but I'll briefly mention many of them. And when we talk about the chemistry, we're going to focus on the most common ones. So about 20 to 25% of them. It's not much, is it? About 20 elements are essential for life. The rest of them not, at least in terms of your biomass. So let's have a look at the really important ones then. The really important ones are the ones that make up 96% of your biomass. 96% of your body is made up of carbon, hydrogen, oxygen, and nitrogen. All right, that's a good fact to remember. Shall I tell you a good way to remember little facts? So here we've got carbon, hydrogen, oxygen, and nitrogen. Yep, just make up little words from the first letter of each of the words you've got to remember. So this word chon is how I remembered it. Chon, carbon, hydrogen, oxygen, nitrogen. Chon is 96%. Write that down, look at it a whole bunch of times, maybe write it down 3 or 4 times, and you've remembered it. It's a quick sort of little memory technique. I don't know, can you make another word from carbon, hydrogen, oxygen, nitrogen? Make another word from those letters. Make another one. Honk, that's a good one.
Hey.
Honk. Okay. Now what's nice about honk, how many chemical bonds does hydrogen make? 1. That's the first letter. How many chemical bonds does oxygen make? 2 is the second letter. How many chemical bonds does nitrogen make? Typically. And carbon? There you go. All right. So most of the remaining 4% is made up of calcium and phosphorus and potassium and sulfur. Not in elemental form, all right, but as compounds. Now, of course, 96 and 4% add up to 100%, but we've got these trace elements that are present in tiny, tiny, tiny amounts, tiny quantities. They're critically important, they're essential to your existence and survival, but they're only present in tiny amounts. And I'll give you some examples of those in a moment, but a nice example is iodine. Right? Iodine is considered a trace element. You only need it in minute amounts. What kind of foods are rich in iodine? Ah, so have you seen on a salt container, it says iodized salt. Yeah? So as the food industry floods us with chemical foods that are devoid of a lot of natural nutrients, yeah, one of those happened to be iodine. So typically our diets, especially in first world countries and many third world countries, are not good. And so the food you eat doesn't contain the nutrients you need. Iodine seems to be one that's kind of lacking in our diet. And so what they've done is they've made salt, table salt, sodium chloride, which has iodine in it. So table salt you get is not just sodium chloride. There's other trace elements in there, one of which is iodine, because it's a very important one. But what foods does it naturally occur in? Somebody said it. Seafoods. Yeah, seafoods. So many shellfish, okay, have lots of iodine in them. I think broccoli does as well, have a lot of iodine in it. All right? You like broccoli? I do too. All right, so let's see what happens if you don't get enough iodine in your diet. All right? So this woman, see that big swelling on her throat? That's a goiter. All right? And goiters result from an iodine deficiency in your diet. Now, iodine is an important part of this molecule. And this molecule is a hormone called thyroxine. All right? How many atoms of iodine does a thyroxine molecule have? Yeah, 3. 1, 2, 3. That's quite a lot of iodine in a molecule. All right? 3 atoms of iodine in each thyroxine molecule. Now, thyroxine is a hormone that your body produces, and it regulates your metabolism. In fact, it does a lot, but it sort of regulates your metabolism. Now, if you don't have enough iodine in your diet, you don't make enough thyroxine. Okay? Now, here's what your body does to respond to that. Thyroxine is made by which endocrine gland? Anyone know? The thyroid. And the thyroid gland is right here. In fact, there's your Adam's apple. Well, if you're a guy, you got one. Right? But you can just go below your Adam's apple, and it's right in here. You can hardly feel it. It's got 2 lobes to it, right? And that's what makes thyroxine. Now, if you don't have enough iodine in your diet, there's not going to be much iodine in your blood. So your thyroid gland grows. Grows and grows and grows. That way it gets a richer blood supply. And what little iodine there is, it's able to pull it out to make the thyroxine that it needs. Okay? So the goiter...
Just enlarging to compensate for her lack of iodine.
Yeah. The goiter can go away if the iodine comes back. All right? Okay, so that's a good example. You don't need much iodine in your diet, let me tell you. You need a very tiny amount. But the consequences of not having enough of these trace elements can sometimes be really significant. Okay? All right. Good?
What about if you had too much iodine?
Yeah, that can cause a problem as well. So some folks go overboard on supplements, right? Nutrient supplements. And kelp happens to be very rich in iodine. All right? So if you take too much iodine, what do you think happens to your thyroid gland?
It shrinks.
Kind of shrinks a little bit, yeah. And sometimes you can actually not produce enough thyroxine. All right? So you've got hypothyroidism and hyperthyroidism, 2 conditions. All right, so let's have a look at all of these elements then. There we've got our big 4, all right? Oxygen, carbon, hydrogen, nitrogen. There's the symbol. There's the percentages that they do occur in your body. It's kind of remarkable, isn't it? You're 65% oxygen. You're 65% colorless, odorless gas. Yeah? When you reduce yourself down. Carbon, you're about 18%. All right, so that forms about 93. Then we've got calcium, phosphorus, potassium, sulfur, sodium chloride, magnesium, form about the other 4%. You can see their absolute values there. And these are some examples of the trace elements. All right, so boron, chromium, cobalt, copper, fluorine, iodine, iron, manganese, molybdenum, selenium, silicon, tin, vanadium, zinc. Have you ever seen a list like that? Where would you see a list like that?
What's like a nutrition fact for a person to me?
It looks like a...
Like a person's nutrition fact or something.
Okay. If you go to the store, if you go to Safeway right now, where would you find a list of those on some... Sorry?
Medication.
Yeah. So these aren't vitamins, but if you look at... Because that's the right way to say it, vitamins, not vitamins. But anyway. If you have a look at on a jar of multivitamins and minerals, most of those are listed under the mineral list. And it's to compensate for, obviously, a diet that's deficient in them. All right. And most college students exist on pizza and Pepsi, right? Maybe beer, depending on how old you are. And they don't have that full repertoire of essential elements. So. Okay. Good so far? All right. So now let's look at concept 2. We're going to have a look at the atom and subatomic particles. We're going to see what is matter made up of. So, atomic structure determines the behavior of an element. The structure of the atom determines the chemical behavior of the element. So what I want to do is have a look at the structure of atoms. each element has a different atomic structure, or at least the parts of the atom. Number of them vary. All right, so an atom is the smallest unit of matter. An atom is the smallest unit of matter. And we can take any chunk of matter and break it down into its different atoms. But atoms themselves are made of even smaller particles that we call subatomic particles. So what are the subatomic particles that make up atoms? Yeah, those three are?
Neutron, proton, neutron, although I think he said neutron here.
Oh, I missed out the T. That's criminal, isn't it? I missed out the T in neutron. It's neutron, not neuron. I was thinking nerve cell. I'm too much biologist, not enough chemist today. This is how you spell neutron. Maybe that's how we came up with neuron. Somebody made a spelling mistake and left out the T. So, the subatomic particles that make up atoms, in fact, there are a whole bunch of them. There's more than just this, but we're going to talk about these. They're the biggest, I guess, and probably the most important to what we're going to talk about. So we've got neutrons, and neutrons, as the name implies, are neutral in charge. Then we've got protons, small little subatomic particles that have a positive charge, and electrons, which are teeny tiny subatomic particles that have a negative charge. Now, I just want to talk about charge for a moment. Think about charge as a property that these particles have. Now, here's where it becomes relevant and important. If I have something that has a positive charge, what do we say about charges?
What do you mean?
Opposites attract,
Oh, yeah.
right? With charges, opposites attract. So if I've got something that has a positive charge and something that's got a negative charge, and they come close together, what's going to happen? They attract. Just like the positive and negative poles of a magnet. They get pulled together, they attract, right? If I have two positives close to each other, what are they going to do? They're going to repel, all right? Same with two negatives. They're going to repel. So it's a property that the particles have, and here's where it's relevant. If they're opposite, they're going to attract. If they're the same, they're going to repel. Okay? So what about a neutron that's got no charge? It's neither positive nor negative. What's going to happen if a neutron comes up against this one?
They're going to bump.
Just with respect to charges.
The neuron will give its charge to the opposite, won't it?
If this has no charge,
It's not going to have a charge. It's just going to...
and it comes in close proximity to this, which has positive charge, how are they going to interact?
Go away.
There will be no interaction. Okay? The neutron is negatively charged. It's not affected by this in the least. It's neither repelled nor attracted. Okay? Is everyone okay with that? Let's just say we have a neutron that comes close to this one, which is negatively charged. How are they going to interact? Neither attracted nor repelled. What about if we have two neutrons that are in close proximity? How are they going to interact?
They're not.
They're not. There will be neither attraction nor repulsion. Good? So based on the charge, now you know how particles are going to interact with each other, yeah? If they're opposite, they're going to attract. If they're the same, they're going to repel. If there's no charge, then there's no real interaction. Okay? All right. So now we're going to look at how these subatomic particles, the neutrons, the protons, or electrons, are arranged in an atom. So neutrons and protons form what we call the atomic nucleus. So an atom has a nucleus. It's at the center of the atom, and it's where you find the protons and the neutrons. Okay? Electrons form a cloud around the nucleus, and they're in motion. In fact, they move extremely quickly around the nucleus in this electron cloud. Okay? Now, neutrons and protons, they both have a mass, as do electrons. And the mass of a proton and the mass of a neutron is about the same. In fact, neutrons are very slightly heavier. They've got slightly greater mass than protons, but they're almost the same. And we've got a unit of measurement called the Dalton, which we use to measure subatomic particle mass. And I'll give you that value in a moment, what the masses are and what a Dalton is. Do we have a balance that can measure down to the Dalton level, do you think? We absolutely don't. But we can get at their mass in a lot of different ways. All right, so I want you to draw an atom. I'll draw one on the board, and we're going to just draw a generic structure of an atom. Okay? So what's at the center? The nucleus, which is made of protons and neutrons. Now I'm going to have a hard time drawing this next bit because I've got to draw a cloud around it of electrons. So I'm just going to kind of scribble it roughly. Don't draw this. All right, so there's a cloud around the nucleus where the electrons are, and the electrons are kind of flying around. So I'm going to give you a slightly, I guess, more tangible rendition of what the atom looks like, although it's not realistic to what a real atom looks like. Okay? So atoms at their center have a nucleus. And they have electrons which fly around them. All right? So I'm going to draw it like this. There's an electron, there's another electron, and I'm going to say that they kind of fly around like this. They zoom around. They don't really do that. Is everybody okay with that? They really don't. But from here on out, I'm going to represent electrons as though they fly around the nucleus in a similar way that planets orbit the sun. Okay? That's not how it really works, but it's easy to understand in that way. Good? Okay? So electrons fly around in orbitals, or shells is what we're going to call them, around the nucleus, which has the P's and the N's. Good? Everybody okay with generic atomic, the structure of a generic atom? Yeah? I think it's pretty straightforward. All right, so I'm going to show you this little video clip. We might play it all.
Hi, I'm Emerald Robinson. In this 1 No two elements have the same number of protons. Revolving around the nucleus like planets around the sun are negatively charged particles called electrons. Electrons and protons attract each other, so atoms usually have equal numbers of the two particles. Scientists assign atoms an atomic number, an atomic mass unit. The atomic number is the number of protons present in the atom. For instance, a helium atom has 2 protons, so helium's atomic number is 2. Add the number of protons and neutrons in an atom's nucleus together, and you get the atomic mass unit, or AMU. A helium atom has 2 protons and 2 neutrons, so has a mass of 4 AMU. Electrons have almost no mass and are not included in AMU calculations. While an atom's number of protons remains constant, individual atoms can lose or gain electrons. Atoms with different ratios of electrons to protons are called ions. Atoms of the same element can also have extra neutrons. Scientists call atoms with extra neutrons isotopes. Despite having different neutron counts, isotopes retain their element's chemical properties because the number of protons remains constant.
For thousands of how-to and advice videos on any topic.
Did you get all that? First part you did, didn't you?
Last
And the-
part was very dense.
And the rest of it was quick. But we're going to look at each one of those topics bit by bit and make sure you understand it. Okay? Might play it all. Right. I've got to start the narration again. Okay. All right. So here we've got an atom. Let's just review it. Nucleus is overall what charge? It's overall positively charged. Why is the nucleus overall positively charged? Because the protons. Do the neutrons affect the charge? No. All right. So the cloud of electrons, what charge are they? Negatively charged. Good. So there we've got our nucleus made of protons and neutrons, and there we've got our electron cloud. We spin around the nucleus, our electrons. Okay? So this is how I'm mostly going to represent atoms. I'm going to draw a nucleus in the middle. I'm going to draw electrons that seem to fly around in this orbit around the nucleus. But probably closer to what really happens is, well, at the center we've got our nucleus positively charged, but the electrons form a cloud. All right? It's a little bit more accurate is what's really going on. So in the case of this atom, how many protons do we have in the nucleus if the protons are that pinky color? 2. How many neutrons it got? 2. How many electrons it got? 2. All right. Okay, so we've got our subatomic particles, neutrons, protons, electrons. We know the charge of them. Now here's their mass in daltons. All right. So a neutron is just over 1 dalton in mass. And a proton is very slightly over 1 dalton in mass. But look at the electrons. 1/2000th of a dalton. Tiny mass by comparison. And a dalton is a number. It's a unit of mass measurement that we apply to these subatomic particles. And a dalton is about 1.66 times 10 to the negative 24. So if you wanted to write that out, how many zeros would you put in there? 0 point, I'm not going to draw 23 zeros, right? 23 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3. 1, 6, 6. Of a gram. That's a tiny amount. Yep. Okay, so atoms, you know what their structure is. There's a nucleus, the electrons fly around. In the case of an element like helium, this is what a helium atom would look like. Okay? Now I want you to have a look at the periodic table of helium up there. Those of you that are far away, you might not be able to quite see it. Those of you that are close, what are those two numbers associated with helium? What are those two numbers associated with helium? Now have a look. Tell me what they are. No, tell me what the numbers are.
You have 2, and then you have 4.002.
Good. Let's round it.
So just 4.
2 and 4. They're the two numbers associated with helium. Good? All right. So we've got the number 2 and the number 4. Now have a look at these atoms. All right. So how many protons does helium have? 2. We'll see the number up there in the periodic table, the number 2. That tells you how many protons each element has in its atoms. Helium has 2 protons, so we've got that number 2 associated with it. The other number 4 in helium, what do you think that could represent? Have a look at the helium atom. What could it represent? Don't tell me its name if you know it. Tell me what it could be, what it could equal.
The total number of both protons and neutrons.
So look in the nucleus. 1, 2, 3, 4. It's got 2 protons, 2 neutrons. Add them together, we get 4. Okay? And there's our number 4 with helium. All right. So atoms of different elements, they differ in the number of subatomic particles they got. They vary in the number of subatomic particles. Helium, for example, has a different number of subatomic particles than does oxygen, or hydrogen, or nitrogen, or carbon. Each element has a number associated with it called its atomic number. And the atomic number is the number of protons in the nucleus of that element. All right? Okay, so in the case of helium, that number 2 is the atomic number for helium. All right? Now, on the periodic table on the wall, the atomic number is the smaller number of the 2 in red above the elements symbol. Okay? So let's take carbon. What's the atomic number of carbon? 6. Yeah. So how many protons does an atom of carbon have? 6. What about nitrogen? What's its atomic number?
7.
How many protons in an atom of nitrogen? All right, what about oxygen? What's its atomic number? So how many protons it got? 8. And where are the protons? All right, good. So now let's take something like iodine. Atomic number is how many protons in the nucleus of one iodine atom? That's a big atom, isn't it? Compared to helium, carbon, oxygen, and nitrogen. All right, so the other number associated with the element is called the mass number. And the mass number is the number of protons and the number of neutrons in the nucleus. So for helium, we've already figured that one out, haven't we? How many protons, how many neutrons in a helium atom? 2 protons and 2 neutrons. All right, from the atomic number, yeah, you can, from the mass number, you can figure out the number of protons and the number of neutrons as long as you know the atomic mass. Yep. Right, let's take sodium. The mass number of sodium, if we round it, is 23. So what's the sum total of protons and neutrons in a sodium atom? 23. Good? All right. Now, the atomic mass of an atom is its total mass. The mass number is just the neutrons and protons. But the mass number doesn't take into account the electron mass, does it? The atomic mass does take into account the electron mass. But what we tend to do is we tend to say, all right, well, electrons have such a teeny tiny mass that the atomic mass and the mass number are about the same. Okay?
Is that the number at the bottom?
It is, in the case of these elements on the periodic table, yeah. So the atomic number equals what? Number of protons in the nucleus of the atom. Okay? Now, an atom is overall itself neutral in charge. Okay? An atom itself is neutral in charge. And the protons have what charge? And the electrons have what charge? All right. Therefore, in a neutral atom, and atoms are neutral in charge overall, the number of what equals the number of what? Protons equals the number of electrons, right? The number of protons equals the number of electrons. And their charges kind of cancel each other out, making it neutral. So the number of electrons equals the number of what in an atom? You said it earlier. The number of electrons equals the number of protons. All right, so let's take an atom of chlorine. How many electrons does a chlorine atom have? 17. How many protons does an atom of chlorine have? 17. So 17 positives, 17 negatives, they cancel each other out, making it overall no charge. Okay? All right. Now, the atomic number is usually a superscript before or after the element symbol. Usually. What's another way you can nearly always figure out of the two numbers associated with an element? How can you usually figure out which one's the atomic number? It's a small one. Okay? Smaller of the two numbers. Now, there is one kind of exception. Let's have a look at hydrogen up there. What's the atomic number of hydrogen? What's the atomic mass of hydrogen? If we round it, it's 1. So let's take hydrogen as an atom then. How many protons does a hydrogen atom have? 1. How many neutrons does a hydrogen atom have?
0.
We've got two answers. We've got 0 or 1. What's the atomic mass of hydrogen? 1. Atomic mass of hydrogen is 1. The atomic mass is the number of protons plus the number of neutrons. So how many neutrons in a hydrogen atom? 0, none. Now there are some hydrogen atoms that do have a proton, and they're called isotopes of hydrogen, which we'll talk about in a little bit. All right, so the point of that is sometimes you get into this groove, right, of sort of automated answers. Yeah? Don't. Work it out. Try to work it out all the time from first principles. Okay? If the atomic number is 1, you know there's 1 proton. If the atomic mass is 1, what plus 1 equals 1? 0. That's how you know there was no neutrons. All right. So the mass number equals what?
The total mass of it, including
Neutrons and protons.
The number of neutrons plus the number of protons. Right. It's the mass number. And honestly, the atomic mass is not exactly the same, but we usually look at them as the same because the mass of electrons is what?
Close to nothing.
Tiny. compared to the mass of the protons and the neutrons. Okay, so the mass number is usually a subscript by the element. So helium, we would have the number 2 and the number 4 associated with it. 2 is its atomic number, 4 is its mass number. Okay. And from that, you can tell everything about the electrons and the neutrons and the protons in a helium atom. Okay. All right, so let's round this out by looking at some examples. The element sodium has got a mass number of 23 and an atomic number of 11. How many? Don't yell out the answers. I want you to write them down in your book. How many protons does sodium have? Just write that answer down. How many neutrons does sodium have? And how many electrons does it have? So what are the answers? How many protons? 11. How many neutrons? 12. Does the number of neutrons always equal the number of protons then?
Evidently not.
No, it doesn't. Sometimes it does. Doesn't always. And how many electrons it got?
11.
Good. All right. And that brings us on to this concept of isotopes, which I'll start next time. All right. So, what have you got to remember to do before next week? The online quiz, which I'll post today. I'll usually post them on Thursday, and they'll go offline usually when? Monday night, usually at 9 o'clock. Okay? Make sure you take them, because once that due date and time comes around, what happens to that quiz? It's gone forever, regardless of the reason. All right. Have a good weekend, everybody.